Okay, so they're saying we need to answer all questions. The constants here are given. They always give you the constants. And also for R, you need to be familiar. Since you're doing CHEM1000, you need to be familiar with R values. We only use a particular R value depending on the pressure that is given in a question. Yeah, so let's start with section A. Section A says, answer all questions on the grid provided. Each question carries 12 marks. So they're going to give you a booklet that has portions where you can mark or cross. They'll give you the instructions. Yeah, they'll say on the booklet. Look at question 1. They're saying the recommended limit for safe exposure of sulfur dioxide in air is 0.0004025%. What is the concentration in parts per million in ppm? Okay, so question 1, they're saying I will express this percentage here in parts per million, and a million we are saying has Nimezi, we are saying 6 zeros. So if I may, okay, just a minute. Yeah, so I have 0.000025. That's what we are having. Percent. So this is a percentage, right? We need to express it in ppm. So this is going to be a percentage is always out of 100. We multiply this by ppm, which is 10 to the power 6. Yeah, so this is going to be 1 0 cancels with 1 0 there. Yeah, this is going to give us what? If you punch this on your calculator, are you getting 0.25?
Yes, I am.
Yeah, so this is what we have. So ppm is 10 to the power 6. Then parts per trillion, ppt meaning you multiply it with 10 to the power trillion is 10 to the power what?
I'm not sure.
Yeah, so a trillion would be 10 to the power 12. Yeah, 10 to the power 12 would have been what would have used. Yeah, so this is just a notation that we use. Yeah, it's like they give you a volume, then they want you to put it in a different format, sort of. So this is the answer here should have been option what? Option B, right? The answer there is B. Then look at number 2. Which solution among the following does not contain the same total number of ions? So the first thing that we're going to consider is the volumes that are given, right? So change all the volumes into what? Into liters or decimeter cubed. And when you do that, you're simply going to have your volume like here to be 0.01 liters or decimeter. Then get the moles, right? Get the moles, get the moles, get the moles, get the moles. Yeah, so which solution among the following does not contain the same total number of ions? So the only thing that will come out differently here would be C. If you do the calculation, if you get the moles, then convert those moles to number of particles or number of ions, because the particles here have been described to be ions. We're looking for the number of ions, which is the number of particles. So convert using 1 mole is equal to Avogadro's constant, which is 6.022 10 to the power 23 ions. Yeah, so if you do that, your answer is going to be C. Have you gotten what I've said, Nyumezi?
Yes, I have.
Yeah, so we solve for each part, right? You solve for each part. So the only one that will give us a different answer would be C. The rest will give you the same outcome, the same number of ions. Yeah, so that's what we do. Your answer will be C. Then number 3, the order of the rate of diffusion of gases, ammonia, sulfur dioxide, chlorine, and carbon dioxide is what? So we follow the molar mass. Which one is going to have the least molar mass? That's what we follow. We arrange them in that particular order because that will determine the rate. So let me try to give us the misters. So for ammonia, let me put it here. That's a 17, right? Yeah, ammonia, that's 17. The next guy that comes here is what? We have sulfur dioxide. sulfur dioxide has a 64 as a molar mass, roughly. Chlorine has what? Is it a 71? Then carbon dioxide has 44. Yeah. So the order will be the one that what they're saying, the order of the red gases. So the rate. So the order, this one is first. So ammonia is the fastest, followed by carbon dioxide, then followed by sulfur dioxide, then followed by chlorine. So the answer will be option B. This is okay here, Nimes, right? So that's what you get. The answer would have been B. Then question number A4, they are saying at constant pressure, at which temperature will the volume of the gas be twice what it is at 0 degrees Celsius? So pressure is constant, right? So pressure is constant. Remember that formula that you say P1 V1 over T1 is equal to P2 V2 over T2. So they want the pressure to be constant, so we can remove the pressure there. Then they are saying the initial temperature was 0 degrees. 0 degrees is the same as 273 kelvins, right? Then the question they are saying, at what other temperature will the volume be twice what it was? So the volume should be twice what it was. So we're looking for T2 when the volume now here is 2 times V1 because it's now twice, right? We cross multiply. Our T2 V1 is equal to 546 V1. We can divide by the V1, divide by the V1, meaning our T2 should be 546 kelvins. So our option there is going to be, is it 546? Is it what should be there? It should be C, right? This guy here. Unless if they gave us 273 degrees Celsius, we could have accepted that because it's like we're converting this back to degrees Celsius. So yeah, so that's what you're supposed to do. Then question A5, they're saying which of the following quantum numbers primarily determines the size and the energy of an orbital? Which one here, Nyumezi? This is very simple. We have 4 quantum numbers. Principal quantum number tells us the size of the shell and the energy we're dealing with, the n. So the answer there is B. The bigger the value of n, the more energy needed, right? Then the angular quantum number tells us the shape of the orbital we're dealing with. Magnetic spin tells us the number of each type of orbital we're dealing with. Orientation in space is determined by the magnetic spin quantum number. You remember this, Nyumezi, right? Yeah, so the answer here was supposed to be B. Then look at number 6. Number 6 here, they're saying according to the Pauli exclusion principle. So what does this guy says what? The lowest energy electron configuration is what we're going to consider. So according to Pauli exclusion principle, which atom has the lowest energy electron configuration? Lowest energy is dependent on the number of repulsions we're able to experience on the last orbital. So the one that will be lowest here will be this, because this gives us a lot of repulsions. This, they are minimal because in the 2p slot, we're just forcing 2. The other guys are independent. We just have this, the 4, right? These ones here, we're just forcing. The one that is worse, that has low energy is this guy. This guy here has low energy such that by any mistake, you can remove any electron because they don't want to stay here. They are not stable. They are not happy because you've squeezed them, and they are repelling each other because they are both, or rather all negative on each slot. Negative, just pointing up and down to minimize the repulsions. So this is the least stable one. So the answer there is D. Hope that's okay. The next one is this guy here. They're saying calculate the formal charge of carbon in cyanide. Now, this cyanide we're given here is a bit special because every cyanide on a normal day would have a charge on top, but here there was no charge. So I had to take it as it is. And they want the formal charge of carbon. So we know how we get the formal charge. So I'll write the cyanide how it's given. We have carbon with 2 electrons. This is stable with 2 electrons inside. We want the formal charge of carbon, right? Yeah, so carbon, we'll say Fc is equal to non-bonding electrons are 4 minus the bonding electrons are 6 divided them by 2. The number of lone electrons are 2. Yeah, we have 2 lone electrons. Okay, this is going to give us this gives us what?
31.
4 minus 3 minus 2. This gives us what? A -1, right? Yeah, so we need to get -1. Is there an option there? Yes, this guy, right? Yeah. So the next one, is this okay here? You may as well have gotten the formal charge. Yeah, so please don't forget, we're equating everything to 0 because there was no charge on this CHEM molecule, so that's why we're just doing that. And so formal charge would have just verified it using the charge to say when you get, what's the formal charge of nitrogen in this case, right? If you're looking for nitrogen, would have gotten what? Nitrogen has 5, then minus this would have given us 3 minus 2. Is this giving us what? Okay, this gives us is this true here, Nyumezi? Are we getting a 0 for nitrogen? So if we're getting a 0 here, it just validates what I said earlier on, to say this guy always carries a negative charge, because when you add the formal charges, you should get the charge which is there. So we just want to see if we get all the formal charges of all the atoms, are we actually getting the overall charge? It's like the oxidation number of the whole complex ion. Yeah, so it just confirms what we did to say it was right. Yeah, so look at number A8. A8, they're saying which of the following numbered carbons has an sp2 hybridization state in the structure below? Which of these carbons? Which one? The third one, you're sure? So we have what? We have carbon number 1, we have carbon number 2, we have carbon number 3. So sp2 hybridization forms when? When do we form sp2 hybridization?
What did you say?
Yeah, so the correct answer here has to be what? Has to be carbon number what? We said carbon number 3, right? This has to be carbon number 3 because we have what? sp2 forms whenever we have a double bond. Let me just try to, yeah, so we said sp2 exists whenever we have a double bond, sp3 exists whenever we have single bonds, then we have sp which exists whenever we have a triple bond. Yeah, so this is just what we did. So whenever you see a double bond, just know to say a double bond always symbolizes sp2 hybridization. So that answers our question. Then number 9, A9, they're saying which statement about the galvanic cell is not correct? Which statement about the galvanic cell is not correct? Which one here is not correct? Okay, so here they're saying the first one, let's disqualify them. So which one is not true, right? That was the statement. Yeah, so when we consider the anode is where electrons are produced, so expect it to be negative, right? So the first one is false. They're saying a reaction in a galvanic cell always runs in a direction that gives us positive cell. Okay, so let's see. Oh, they're saying a reaction in a galvanic cell always runs in the direction that gives us a positive cell potential. Then here they're saying reduction occurs at the cathode, and then here we say oxidation occurs at the anode. Then the last one, they're saying elemental metal is routinely converted to metal cations at the cathode. The correct answer here is going to be D, because these guys are true, right? This one is true, that's true, that's true. The one we're doubting is this guy here, right? The reaction in a galvanic, we say they're always going to be positive. That's how we know to say something is, the reaction is happening in a galvanic cell, because if it's not positive, we assume that it's an electrolytic cell that's present. Yeah, so A is correct, B and C are correct. The only option we have there that's lagging is option 4. Is that okay? And then look at the next question here. The next question, they want us to, they're saying what? The standard electrode potentials of magnesium and copper are given. So they've given us the half equations, right? They want the standard cell potential of this. Can you attempt it before we do it together? Okay, so you're getting the answer to be 2.71, which is true, it's correct. Yeah, because we say the easier way to do it, this is under what? This is under section A. They don't even have to see your working, you just have to pick the right thing. So you can just reverse the smaller one, reverse this guy. It gives you a positive 237, then add it to the, so reverse the anode figure and add it to the cathode figure. So that's how we get our answer. Your answer will be A. And the next one, they're saying the reaction has a rate of this with the rate constant being 0.87 molarity per second at this temperature. What is the half-life for this reaction at this temperature when the initial concentration is given to be 0.059? Oh yeah, so we're given the order of the reaction. I mean, from the expression for the rate law, meaning it's a second order reaction, right? Yeah, so if it's a second order reaction, we always say what? The rate law, the half-life. The half-life is equal to 1. Is equal to, we have what? We have K, then the initial concentration. So now the question there is asking about K. K is given. They're saying what? The reaction is as this guy, the rate constant is that. What is the half-life of this reaction when the concentration is? So the concentration is when the initial concentration, that's what we have there. So we just do the replacement. Yeah, so do the replacement is 1, the constant 0.087. And when you're looking for what our initial concentration, so this is what we have our initial concentration, that's 0.059. 194 point. This is roughly the same as 195, right? Yeah, you can just leave it there, so you get something close. So question number A12, I mean, they're saying what is the concentration of the reactant in a first order reaction when the rate of the reaction is the given and the rate constant is given to be this. Yeah, so we're going to get what? This is a first order reaction. Yeah, so if it's a first order reaction, meaning whatsoever we have, the rate is equal to, we say what? K and the concentration of whatsoever A is. There's a 1 there, right? So the rate is going to be given as this guy here, the same one that we have. When the rate of the reaction is this, so the rate is 0.88, the constant is 0.078. We're looking for the initial concentration. So we have this guy here, we cancel it. So when you divide, what do you get?
11.8.
Yeah, so the answer here has to be a C, so this is okay. Then number A13, they're saying if the reaction quotient has a smaller value than the related equilibrium constant, then what does it mean? So what does it mean?
The reaction is not that it is equilibrium, and that there are more reactants than products.
Oh yeah. Yeah, so here the answer is going to be B, right?
Yes.
Yeah, then number 14. Number 14 here we're having, so here they're saying which, given that for the reaction that there's an energy given there, a positive one, and also a constant, which of the following would be true if the temperature was increased from 25 to 100? What would be happening? So the temperature is what? The temperature is increased, right? This is increasing, right? And then this will get bigger. The K gets bigger. The K value has to get bigger because the enthalpy gets bigger as well. So I mean the reaction speeds up because this is already an endothermic reaction, meaning it needs heat for it to happen. Yeah, so here we say what? We say the value of K will be smaller, that's force. The concentration of A will be increased. Then they're saying the concentration of B would decrease. So the answer here would just be, they're saying which of the following would be true if the temperature is increased? The value of K would be smaller. No, one is not. The concentration of A is on the product side, A is on the reactant side, it will not increase. Then C, B, the concentration of B will increase. The answer is C, right? Yeah. The answer there will be C. Okay, so look at the next one here. They're saying if the scuba diver ascends too quickly, the rapid pressure drop causes small bubbles of nitrogen to form throughout the body. A condition called the bends. The law applied here is, what law here is applied? So when a scuba diver ascends, right, they go up. You notice that there's going to be, they're saying a pressure drop causes small bubbles of nitrogen to form throughout the body. This is called the bends. The law here is applied is this law here, Boyle's law. This is the guy who founded this guy. Yeah, so there's Henry's law, there's Rod's law, there's, yeah. So the only law that connects directly to the diver's pressure is simply Boyle's law. That's general rule that says P1 V1 over T1 is equal to P2 over V2. Times V2 then over T2. That formula is the one that works here. So no wonder D is our best option here. Yeah. And the next one. This is very simple here. What's the answer here going to be? Yeah, so the answer here is going to be A, because it's what? It's moving from pressure to gas, that's deposition. Then it's moving from solid, it's moving from solid to gas, right? That's sublimation. Then from gas to solid is deposition, right? So the answer is A, the first one. Then how about the next one? So here they've given us, in a sample of pure water, only one of the following statements are always true. Here they're saying true at all conditions. Temperature, which one? So if you pick A, meaning you can also pick this and this. So the most correct answer here will be D, because the concentration of the hydronium ions, which is H plus, and also hydroxide have to be the same because it's pure water, very clean, no impurities. The pH has to be, we already know it's 7 because the thing is neutral, right? Yes, the more correct answer there would have been D. Yeah. So number 18, they're saying what? They're saying, which of the following structures correctly represents the compound 5-ethyl 2-cyclo 2-hexane 1-on? So we have what? We have, first of all, we have a cyclohexane. So we have, look at the rings that we're having, right? Look at the rings that we're having. So you can call this to be what? This is, call this to be 1. That's 2. So I think this satisfies, right? We have a 5-methyl, 1, 2, 3, 4, 5. Yeah, so correct answer here is what? The correct answer here is 1 there. Yeah, so this is what you get. Because you look at the position and the numbering as well that they gave us. Yeah, so B and C are only different from A because of how they position them to be. Hope that's okay. Then look at number 19. Among the following reactions, which ones accounts for the formation of this after reacting the ethine? If we're reacting this, if we're saying for the formation of this, how can we create this? Meaning there are 3 bromines and one looks like, so we have what? We have the formation of this after ethine. So if you say what, which ones here? Imez, you're saying what's your best shot here?
I said I would have guessed maybe A or C.
The correct answer here will be C. Yeah, because if we want, why C? Because we want to replace this guy here. We need to have those reaction mechanisms. Yeah, because we're having what? We're having chlorine. There's a chlorine there, right? Even here there's a chlorine. And the one that's more reactive between bromine and chlorine is chlorine. So it's better that it stays alone. Okay, yeah, so this is going to be, our correct answer here is only C, because if I write the ethine that they're talking about, you know ethine, right? Ethine, where this thing is coming from. Ethine, where this whole thing came from. Ethine is ethene with a triple bond, so it's supposed to be like this. We're supposed to have something that looks like this. This is literally what was there present. Then they reacted this with, we can say first of all, HBr. So in the reactive with HBr is going to be this with a double bond now with the what? With an H, a Br with an H. Then react this with chlorine, it opens up, so you're going to get what? Let's see what they got. And we need 2 bromines. We need 2 bromines and 1. So I'll go with this. It's supposed to be this. Because we need 2 bromines. There's a Br and a Br, right? Then we have 1 chlorine. Yeah, so the answer here is B, Nyumezi. Yeah, it's B, yes. Because we need 2 bromines and we need 1 chlorine. So yeah, the answer has to be B. Because now we're going to add, so it has to be done in an order where we have, yes, HCl, comes in, so it unlocks the triple bond and makes them to be like this. Then we have H and H. Then we're going to get BR2. Okay, so we say we have this. Hydrogens we have 3, right? 1, 2, 3, 1, 2, 3. Bromines we have 2. This, yeah. So this is what we get. So these 2 are the only ones that can do what we wanted. Yeah. So the answer is this. Hope this makes sense here. You measure, right? Yeah. Then the last one, they're saying what? Which of the following statements is incorrect about electrophiles? So we need to say electrophiles are electron deficient species because these guys are positively charged, right? They want electrons, they want to bond with something. They attack the proton rich parts of the molecules. They are skeletal, or they are what we can say their lowest structure is simply acidic in nature. It's not, yeah, it's not basic. Yeah, so the correct answer here is this. That's a wrong statement here that you can think about. Is this okay? Yeah, so this is going to mark the end of section 1. Marks the end of section A. Now let's go to section B. So section B, they were saying cyclobutane has the empirical formula CH2. Its molar mass is supposed to be, this was supposed to be what? 42 grams per mole, right? Yeah, so this paper had a lot of errors. They corrected them, I think, during the paper. Yeah, so they do make corrections even during the exam because they make typos as well. So yeah, so cyclobutane has this empirical formula. We want to get the actual molecular formula. How do we get it?
You get the mass of the empirical formula. It's N H2N.
This gives us what? A 2, and this is a 12, that gives us 14, right? Then you write properly to say CH2, write an N there, should give us 42 grams per mole. This is going to be N with a 12, then plus 2N. Then you have 42. This is what? 13 is equal to 42. So our N is equal to, when you divide this, what do you get? 3.2. Okay, something like this. So we're just saying approximately our N should be a whole number, which is just 3. So we just say
the values from the actual value gives you 2.9.
Okay, 2.9, which is okay. Yeah, which is just a 3 as well. Okay, so you simply have this. This is going to be the structure of your, I mean the formula of your molecular mass, the molecular formula that was needed. Yeah, so this is what you get. Yeah, this is the molecular formula. Then look at the next question, B2. So B2, they are saying 90 grams of iron trichloride reacts with 50 grams of hydrogen sulfide. What is the limiting reagent? How do we get the limiting reagent here? Nyumezi, can you try it first before we do it together? Okay, here Nyumezi, you are saying we need to write the F. the ion, we wrote the FeC, the chlorine, which is what we have what, plus the H2S to give us what? To give us Fe2S3, right? Plus HCl. Then if we were to balance this, S6 here, right? This is balanced, isn't it? So if you get the moles of, okay, so the mister here, I'll use rounded off one. So the mass here was given to be 90 grams divided by the mister. The mister is 162.2 grams per mole. So the moles that I'm going to get here are 0.555 moles. Then here, when I get the mass, which is the 52 over the mister, which is what? Is it a 34.0 something? Divide these two, I'm getting a 1.526 moles. These are the moles. Then you divide by the integers in front, right? You divide this because the number of moles you've gotten is for 2. So divide it by 2. Same applies here. Divide this guy by 3. So you get what number here if you divide them by, if you divide the first one by 2.
0.2775.
Like this?
0.2. Not 0.2.
Or 0.2, okay. Then the other one will be what?
0.508.
0.058. 0.508. So if you check the ratios in terms of them being put in 1-to-1 ratio, the moles of the ion is less, right? So the limiting reagent here is going to be this guy. This is the limiting, right? Then the next one here says calculate the density of a gaseous hydrogen at a pressure of 1.32 and a temperature of 218. How do we get the density? What is missing? What do we need to do? B4, right? They made a typo here. This bonus, it was not supposed to be there, right? Yeah, so the pressure is given and the temperature is given. So we're going to use this formula, which is just a modified version of the gas. This guy, nRT, when you make number of moles, change it to mister, mass over mister, then because we're given what we're looking for, density. So yeah. So if you punch here, if you try to evaluate this, what density did you get? Because density here would have given us what? The pressure, the mister, over then got what?
0.148.
What were the units? So we can just, let's show the units. Let's show this. The mist of hydrogen is what? What did you use? 2 or what? The gas constant you picked is which one?
I picked the 8.314.
Because the pressure is in atm, so let's look at this guy here. The pressure is in ATM. So go with this guy. We'll use this one here in your maze. This is the guy that we're using because of the pressure. It just makes sure that we get the correct units. Let's just see. I want you to see the dimension analysis that's going to happen here, because we have liters. This is ATM. So for chem, it's always expected of you to show the units. Otherwise, they'll just mark your thing wrong. The temperature was given as what? The temperature was it 218.7? 218.7 kelvins. Yeah, so from here now, we can just try to, I want to just cancel the units so that you see how the density thing is going to come out. So the more part cancels out, the ATM part cancels out, the K and the K part cancels out. You see how we get grams per liter, only grams per liter remains. Yeah, so that should have been our answer here. This is grams per liter, but then you need to use the correct R value to give you the correct thing, because the R value you used is for a different type of pressure. Yeah, if you use that one actually is used when the pressure is not even given in the question most times. So yeah, is this okay?
Yes, it is okay. Then the answer can just be 16.055 liters.
Okay, yeah. When you use the R value, that's correct?
Yes.
Okay, yeah, that's what you get. Yeah, then number 4, B4, they are saying, write the complete electronic configuration for chromium considering any exceptions. So chromium has what? Chromium has an exception rule when it comes to the configuration. The atomic number of chromium is what? Is it 24? It should be 24. So whenever they give you this guy, we're supposed to show the two versions. The two versions are the expected one. We write expected one, and we write it like this: 2p6. This is 3s2. Then you have 3p6. The 2 there. This is going to be 4s2. Then you have 3d4. That's what you get. Then the actual one is 1s2, 2s2, 2p6, 3s2, then 3p6, 4s2, 4s1, and 3d5. So we get one electron from this guy here. We get one electron from the 4s and put in the 3d, because there's no way the 4s can be happy when the 3d has not even reached half. Is this okay? Yeah, so this also is applicable for copper. So these are two exceptions that they like asking. Yeah, so you need to just be familiar with these two. It's always a must. Whenever they give you this, you always have to show the exceptions in terms of writing the actual and the expected one. Yeah, so look at B5. B5, they are saying consider isoelectronic series. So isoelectronic series are simply these guys that have obeyed the octet rule by either gaining or losing, and we have to arrange them in the order of their increasing ionic radius. Yeah, so which order here are we going to follow, Nimezi? What was your thinking?
I said that malaria would be first, because magnesium loses the most iron, followed by sodium, fluoride, and lastly oxygen
Okay, so if I'm getting you properly on what you're saying, so look at the charges that you have. The tricky thing here is that they're all going to be having what? They're all going to be having the same number of electrons, which is 10 electrons. So no wonder they're also falling under the same category, isoelectronic. But the one that's more electronegative in terms of, we look at the charges. So whenever you have this type of a scenario, look at the charges. So the one that has increasing, mean this one will be the smallest because of the pulling that it's doing. In terms of 2 electrons it will have. So the order is just going to be what? The order is still going to be the way it is. Is it the reducing power? So we take it the way it is. Yeah, we take them according to the powers. This is the smallest, followed by this, this is going to be the biggest, because if you look at all of them, they are having 10 electrons in total. Yeah, so the reason why oxygen comes first and we say it has shrinked because of the attractions you're going to experience. Its effective nuclear charge has been lowered, so meaning the pulling is too much, shrinking the whole atom, the whole ion, I mean. That's why it's going to be small as compared to the other guys. The other guys did not technically shrink that much in terms of sodium and magnesium, because they just had to lose for them to have the same 10 number of electrons that these guys had to gain for them to have. Yeah, so hope this is okay. Does this make sense a little bit?
Yes. But there I did for the judgment for law.
Pardon?
Since I use the fifth magnesium has not come to the test.
Yeah, it's the same thing, yeah. Yeah, so we can have that. Then look at this guy here. Given the standard electrode potentials, arrange the highlighted details in the increasing of the reducing power. So in terms of the reducing power, we know why, we say the smaller one. Whenever we're doing our cell potential, we always put the smaller one on the anode side, right? Because it's easy for us to convince it to lose electrons. So we say where we have the anode is where oxidation occurs, right? That's where the reducing agent is. So that's the reducing power. So we want to look at the one that has the smallest value. That's the strongest guy in terms of the reducing power. So the smallest here is going to be what? Which one is the smallest? Is it this guy? Yeah, so this is the smallest, followed by this guy, then followed by this guy, then followed by which one between these two? Followed by this guy. The last one will be that one. So that's the order. This will be 1, this will be 2, that will be 3, that will be 4, then that will be 5. Yeah, so they're saying, in the increasing, so just flip the list. The list I've given you, just flip it. Yeah, because I've given you in a decreasing order. Yeah, so the one that has a smaller value is the one that's strong in terms of the reducing agent. Oxidizing agent, in terms of oxidizing power, would have done the opposite. The one with the highest, or the positive, is the one that's strongest in terms of oxidizing. Just shift, or rather turn the list the other side. Yeah, is this okay? Yeah, then look at B7. B7, they're saying match the given boiling points to the given hydrocarbons. We have what? We have 36 and 9. So we have N-pentane and we have neopentane. Neopentane is made up of a tertiary carbon, because we're having O alkyl group. This is a tertiary carbon because there is no hydrogen bonding to this guy. There is no hydrogen related to this chiral carbon. So that's the reason why we're saying it's neopentane. So neopentane is going to have the smaller value because it's easy to attack it. They are all well outlined. So neopentane is the one that's going to have the 9.5. Then this guy will have the bigger one, which is the 6.2. Because to attack this guy, we have to go bond by bond. Bond by bond, right? This guy here, they're all exposed. We can attack here, break these guys. easily using this. But here we have to follow the order. Break this bond, so it takes time. So no wonder the boiling point is high. They didn't say explain or anything, just match the boiling points to the correct molecule. Yeah, so hope that makes sense in terms of the reasoning. Is that okay? Then this one here, they're saying during a phase change from liquid to vapor, so liquid to vapor in a phase diagram, for example, state whether the following variables would increase, decrease, or remain constant. So enthalpy is the heat. If you are changing something from liquid to vapor, obviously you have to increase the heat, right? Yeah, so it increases. Entropy is the chaos that happens, like the disorderliness of things moving up and about. And if you're moving something from liquid to vapor, the disorderliness gets worse. It increases as well. So entropy increases, enthalpy, they both increase. Yeah, so enthalpy is just the energy. It has to increase to convert a liquid into a vapor. Entropy is the chaos that is going to exist, and it also increases because we are changing from vapor to gas. Then B9, they're saying state two quantities that must be measured to establish the rate of the reaction. Yeah, so two quantities are going to be what? We say the rate is equal to what? The concentration, the change in the concentration of the reactants. So just say the concentration of reactants and time with respect to time. So we just focus on these two things. Remember that equation you are writing, the change minus changes in the concentration of A with respect to time. Yeah, those initial primary definitions of the rate, we used to write something like this: the change in concentration of the reactants over time. These are the two things we need to put in place before we do any calculation. Is this okay?
So after number 10, can I read the code?
After number what?
The question, the answer number 10.
Number 10. Can you what?
Read the code.
Sure. Okay, so number 10, they're saying this is a narrow spectrum antibiotic, penicillin, antibiotic used to treat infections caused by suspectable bacteria. It is a natural penicillin antibiotic. They just want us to get to identify two functional groups that you can see in the structure, right? Yeah, so which functional groups can you see here? There's a carboxylic group, any two that you can see. There's a carboxylic group this side. You can see a key. There's a what? Amide, right? Yeah, there's an amide, this guy here. Yeah, so you can have that. So this was what? This was section B, isn't it? Okay, so let's end here on section B. Okay, so we're going to continue with part C in the next session. Thank you so much for your time.